Well, I was going to announce the speaker, right?
Well, I delegated the task to me today. So you missed the behind the scenes chat, Alex. Okay. Yeah, so welcome everyone to the next talk in the variational analysis and optimization seminar. Today we have Oliver Stein as our speaker. First of all, let me just say a few quick housekeeping things. So if you have a question, just indicate in the chat and we will moderate them through the questions at the end. Please keep your microphones muted during the talk, and also, just so you know, this talk is being recorded. So having said that, maybe you can just make sure everyone is muted. So our speaker today is Oliver Stein, who is professor at the Karlsruhe Institute for Technology in Germany, where he's the head of the continuous optimization group within the Institute for Operations Research. He's an expert in the development and implementation of optimization methods and has particular expertise in semi-infinite optimization, Nash games, parametric optimization, mixed integer nonlinear programming, and multi-objective optimization. And some of that we'll hear about today. And he also has a really nice textbook, Operations Research, that I really like as well. So without further ado, Oliver, the stage is yours.
Thanks very much, Matthew. And thanks for giving me the opportunity to report on our recent results here on branch and bound for multi-objective optimization. So when I was asked to give a talk in the seminar, first thing I said is, but I'm not doing variational analysis at the moment. I cannot contribute there. Then Alex said something like, well, you find traces of variational analysis anywhere. So actually, okay, where's my next slide here? Okay, yeah. So this talk may contain traces of variational analysis. And as you may also have noticed, we have 100 slides here, but this is due to the fact that this is a very graphical talk. It's rather a picture book, like the subtitle says here. That's because I want to convey the ideas here, and I have to introduce many ideas before we can really come to our results. And I will try to do this graphically. So we will have, it's almost like a movie, what I'm trying to present here, right? And this is joint work with Gabi Eichfelder, who's really the expert in multi-objective optimization and makes sure that things that I'm telling you here are really founded in multi-objective optimization. I just entered the field about a year ago. Peter Kirst is a former PhD student of mine who is an expert in branch and bound, and our joint master student Laura Meng was doing the implementation. Actually, the paper is available on Optimization Online since Monday this week, so since 2 days, so brand new research, if you like. But we were working on that for, as I said, for a year. So I give you a very lengthy introduction before I can really tell you what the news here is, which is a sandwiching argument for the so-called non-dominated set. I'll introduce that for the multi-objective problem. And this will also give rise to a branch and bound termination criterion and node selection steps, which is something which is still missing so far in multi-objective branch and bound. And I'll give you some numerical illustrations. So what are we talking about? A multi-objective problem, MOP. Looks like a usual optimization problem. The only difference is that the objective function f here has m entries. So actually you have m objective functions at the same time. And of course, one has to say what this should mean then to minimize such a vector of functions. We'll come to that. And you have the usual constraints. X is a box, capital X is a box. We'll need that for numerical reasons. And G are nonlinear inequality constraints. And in particular, we don't have any convexity assumptions, right? So branch and bound is usually used for non-convex problems, so we don't make convexity assumptions. Now I give you a very brief description of what we're doing with a lot of terminology which has not been introduced, but don't worry, I will introduce everything here. So there is branch and bound for single objective optimization. It's well known how this can be done, and people have tried to transfer this to multi-objective optimization. But the train of thought of branch and bound and single objective optimization hasn't been carried over to multi-objective branch and bound all the way. And that's the gap that we are trying to close here. So in particular, what you need in branch and bound are partial lower bounds on some sets. I'll introduce that, and overall upper bounds. And these were introduced for discarding tests. So you can throw away certain parts of the feasible set by discarding tests. And this has been done already. But in single objective branch and bound, you also obtain overall lower bounds from these partial lower bounds. This has not been done yet in multi-objective optimization. Once you have that, you have this sandwich, which you can use for node selection in branch and bound, and also for termination criterion. And in this talk, we will propose a way to close this gap. So there's not too much literature on branch and bound and multi-objective optimization. Basically, these 5 papers here. So I will not comment on all of them. Let's say Fernandez and Todd were the first to suggest something in 2009 based on interval analysis. We'll also come across that later in the talk. And Gabi Eichfelder, together with her PhD student Julia Niebeling, have the recent publication on branch and bound, where the alpha BB method from single objective optimization was used for discarding tests that appeared in SciM optimization last year. Okay, now let's let the picture book start. So I will give you an introduction to single objective branch and bound first, because I need all the steps to tell you later what has been done already in multi-objective optimization and what has not been done, and or what we do differently. So I will briefly remind you how single objective branch and bound works. So we have a complicated non-convex objective function f here, a one-dimensional feasible set M. And of course, you see the optimal point is over here, and it has an optimal value v. So you evaluate the objective function at the point, you get the optimal value, which is v. And one way to define optimality of this point is to say that no feasible point, that's a negative formulation, no feasible point has a better objective function value, right? That's clear. So first step in branch and bound is that you subdivide the feasible set into many subsets. Every time you see a prime in this talk, like here in the M prime, this will refer to a part of the feasible set, a partial set. And what do you do on these sets? You compute lower bounds on the objective function, right? Like these, on each of these intervals here in one dimension, you compute a lower bound on the objective function somehow. Like with a convex relaxation of the function, like with alpha BB technology, or reformulation-linearization technique would give you a polyhedral relaxation. There are duality arguments. So there are different ways to come up with these lower bounds. LB for lower bound with a prime, because it's different on each of these subsets M prime. What can you do with these lower bounds? Well, you need an additional ingredient. You need some upper bound, which you get by knowing a feasible point. So you have to know a feasible point, X, maybe over here, some totally unrelated to the optimal point. And of course, if you evaluate the objective function at the feasible point, you get an upper bound on B. And now the first interesting step of branch and bound happens. You can throw away all these boxes M, intervals M prime, where these lower bounds exceed the upper bound, like these 3 ones here. Now they have gone away because their lower bounds exceed the upper bound. So the optimal point cannot lie in these boxes. And you only need to keep a list of these subboxes whose lower bound does not exceed the upper bound. And in some of these boxes, your optimal point or the optimal points have to lie. Now, what's next? From all these lower bounds, prime, you can compute an overall lower bound on the optimal value, which is simply the smallest of all these partial lower bounds. I go back one slide. So the smallest of these lower bounds is on this larger box here. And the minimum of all these lower bounds is the overall lower bound. Now you also have an overall lower bound on B. You have an upper bound, a lower bound, so altogether that's a sandwich. Yeah? You sandwich the value B between this overall lower bound and the overall upper bound. This is something that we want to transfer to the multi-objective setting. And as I said, people know how to come up with upper bounds. I will tell you how, but this overall lower bound wasn't considered yet, so people couldn't talk about these sandwiches yet in multi-objective optimization. The usual termination criterion is that the sandwich is thin enough, so the difference between upper and lower bounds should drop below epsilon, which is a tolerance that you choose as the decision maker. And that's a good termination criterion in the sense that the feasible point that you know, this x, which gave rise to the upper bound, then has a very special meaning, namely it's an epsilon minimal point. It's a feasible point, and of course, as a feasible point, its objective value exceeds v, but it also is bounded above by v plus epsilon. That's an epsilon optimal point. You get this from the termination criterion ub minus lb is smaller than epsilon. Now, what if ub minus lb is not smaller than epsilon? Then you have to branch something. Let's skip that. So what do you branch? You usually take the box which is responsible for the lower bound, where the lower bound is so small, much smaller than it should be. Right? So you take this box, branch it, compute new convex relaxations or something to come up with better partial lower bounds. And then also your overall lower bound improves, namely now, so you branched here, but your overall lower bound now is determined by this rightmost partial lower bound. So the lower bound goes up a little. You can also improve the upper bound because during the computations of these lower bounds, probably you found new feasible points. And if you plug in such a feasible point and you get a better objective value, of course, your upper bound also decreases and you see the sandwich becomes thinner. And well, now you can even discard more sets from your list. Go back one slide. This box could not be discarded before, but now your upper bound is smaller, you can throw away this one. And so the sandwich gets thinner and thinner, the number of boxes gets lower and lower, and under some mild assumptions, one can show that this converges. Branching is usually implemented in higher dimensions by looking at the feasible set, which a part of it is described by being x lying in a box, and branching is just implemented by halving these boxes along a longest edge, for example, and then you get your new partial sets. This will not be so important in the following. What will be important is the list of things that you get in branch and bound and what you do not get. So what you have upon termination in branch and bound is, of course, that v lies in the sandwich and the lower and upper bounds have a small distance epsilon. Right? Upon termination, you have that. And among all these partial boxes that are still in your list in the end, all the globally minimal points have to lie. So that's a covering of the set of globally minimal points. And there's a list of things that you don't have. And I'm mentioning this explicitly because people in multi-objective optimization put effort into doing that in relation to branch and bound methods. And our idea is you shouldn't really put effort into that if you just want to transfer the branch and bound idea to multi-objective problems. So what you don't have is that these boxes and the corresponding partial feasible sets themselves become small, or their images that they become small intervals, or that all the points in the partial feasible sets only consists of epsilon optimal points. You don't get that. In particular, these so the first and the third point here are properties in the decision space, and branch and bound doesn't really care about what happens in the decision space. Only this covering idea here is important, right? So branch and bound focuses on the approximation of the optimal value and not of a good approximation of optimal points. You only have some covering of optimal points. You also see that in the picture again here. For example, if you take a feasible point here in this box, which is still in the list upon termination, this is not an epsilon optimal point because the value is up there. So actually, the value is over here, of course, which is far outside of the sandwich, right? So you cannot expect that in branch and bound, and of course, you will not expect that in multi-objective branch and bound as well. Okay, now, preliminaries on multi-objective optimization. So all the pictures here will be plotted for a bi-objective optimization problem. We have two objective functions, f1 and f2, and all the pictures will be in the image space. I don't show you any pictures in the decision space X. There are some notions for the decision space, but since branch and bound only works in the image space, as I just tried to explain, we will do everything in the decision space. So what we see here is the image of the feasible set M, right, under the vector of objective functions F1 and F2. Right? That's the so-called image set. And the first thing that you need in multi-objective optimization is an appropriate generalization of optimality. Right? So optimality in single objective optimization would tell you in the usual definition that a point x bar is optimal if all other feasible points m, x from m, don't have a better optimal objective function value, so f of x is greater or equal. If you say, okay, why not interpret this greater or equal sign as greater or equal between the vectors, you get the following notion. And that's not a good notion for optimality in multi-objective optimization. So we're sitting in the image space here, right? So you check if maybe you have a point x. This is your f of x. And here's your f of x bar, maybe. Right? And this point f of x really satisfies that in the vector sense it's greater or equal than f of x bar, but you also see that there are many other points which do not satisfy that. So this point x bar will not be optimal or whatever you call that. But you see also that this doesn't work at any point, not even over here. Always part of the image of the feasible set laps out of these cones, right? That's not a good notion. So what people thought of is, why not use the negative formulation that I used earlier in single objective optimization already on a slide. Better generalization is that a point x bar is a good point if f of x, for no feasible point x, f of x is strictly smaller in a vector sense than x bar. Right? So then this point would be a good point. So this would be f of x bar, because now in this new cone, in this open cone, you don't find any images of feasible points. Also this point here is good, and also this point here is good. And the right point really poses a small problem, because you have a flat part here of this image set, which means that you can improve this point, f of x bar, in f1 by moving it to the left without changing f2. So actually, if you can improve one objective function without changing the other, this is still not a good notion of optimality. So this is a notion of optimality. It gives rise to the so-called weakly non-dominated set. But the weakly non-dominated set contains these flat parts like this one here, for example. So better generalization is to rewrite the strict inequality from the single objective case as a non-strict inequality together with an inequality, which looks a little complicated, but if you do that in a vector sense, you get a new notion, right? So at these 2 points here, you still have that they are good, but here over in this flat part, this point x bar is not good anymore because these cones are now closed and they overlap with the image set of the objective of the multi-objective problem along the boundary, this horizontal boundary of the cone. Right? So the condition then is violated and these points are ruled out. So this is the so-called non-dominated set of the optimal of the multi-objective problem. In the decision space, the point x is called efficient. In the image space, the images of the efficient points are called non-dominated points. They form the non-dominated set. And altogether, the set is called capital YN in most of the literature now, the so-called non-dominated set. And this is the set which plays the role of the optimal value V in single objective optimization. Right? This is the set that we want to identify somehow by our branch and bound method. So we will also introduce the notion of the generalization of epsilon optimality from the single objective case. And epsilon optimality included this, well, of course, the parameter epsilon. And we do the same negative formulation here that we did for optimality. So this non-strict inequality with an not equal condition at the same time. And this epsilon times E is the all ones vector. So you measure this with the same scaling for all objective functions. So if you don't find x which satisfy this x in the feasible set, then such a point is called epsilon efficient in the decision space, and in the image space that we're looking at, epsilon non-dominated. So this thick blue sets here are the sets of epsilon non-dominated points. The condition here just means that first, if you take this point, you move it over here to by subtracting epsilon times E, and then you look at the cone. And if you don't find image points in this cone, the point that you started with is epsilon efficient or epsilon non-dominated. We will need this notion. And now let's start with a sandwich. Now, the sandwiching property in single objective optimization was that V is enclosed between a lower bound and an upper bound. How can we generalize this? Right? That was the picture. And this is a picture, of course, which shows you the decision space and the image space at the same time, right? But we only work in the image space now, so you only look at this axis. You have the value V over here, and then you have the point LB and the point UB. Right? These are the three interesting points here. And in a set formulation, these inequalities here, these two inequalities, can be rewritten as on the right-hand side here. So the singleton V is contained in the intersection of two sets, where now an important ingredient appears, the set of non-negative numbers, which will become a non-negative orthant in the multi-objective case. So LB plus R plus, of course, is everything above LB, including LB, and UB minus R plus is everything below UB. And V, singleton V, lies in the intersection of these two sets. Not a complicated way to rewrite this inequality, but a way that transfers to the multi-objective setting. Why not try to construct a lower bounding set, capital LB, and an upper bounding set, capital UB, so that our non-dominated set has the analogous property, right? So it's included in the intersection of LB plus Rm plus, so this non-negative orthant, intersected with UB minus Rm plus, right? That would be the set which appears. It's not really a box because it's curved over here and here, right? So that would be such an sandwich enclosure. And of course, LB and UB don't have to be connected. They can have several parts. Actually, later they will be made up of single points. And you see, if you refine this somehow, at least you have a chance to approximate the non-dominated set better and better. We will also need some width measure for this enclosure. And then a natural termination criterion would be that this width is below epsilon. The question is what width, how to define that? Let's start with the upper bound. This is known already, how to come up with a good upper bounding set for multi-objective optimization. So you recall from the single objective setting that you evaluate the objective function at feasible points. And if you find a better feasible point, you replace the upper bound. You improve the upper bound. In multi-objective optimization, that's not always possible, because, of course, this image of a feasible point is better than this one if you minimize both objective functions. But how do you compare these two here, right? So, yeah, R2 is not totally ordered, so that's the problem, right? But a part of this set of red points is good. It's a so-called non-dominated set. So we only keep the non-dominated set of the feasible points that we have so far. This will be denoted by this curvy F, and it's called the provisional non-dominated set. These points are to converge somehow to the non-dominated set. So far, they are only provisional. And now the guess is, if we use this set and add these negative orthants, non-positivity orthants to these points, this should be somehow an upper bound for the non-dominated set. And you see, oops, doesn't work, right? Because everything below here does not contain all the parts of the non-dominated set. So you have to do something else. There's a good solution for that, which is due to Katrin Klamroth and co-authors. You look at the so-called search region, which is defined by this provisional non-dominated set. These are the points which are not dominated by any point from the provisional non-dominated set. So if you take this point here, everything here is dominated, this is dominated, this is dominated, and all the rest is the so-called search region. And what you need now is these formulas for these points here, because if you take the non-positive orthant and add them to these points, you really get this enclosure or the upper bound for the non-dominated set that you're looking for. These are called the so-called local upper bounds, and they can be calculated. In the bi-objective case, it's completely simple to calculate them. Starting with 3 objective functions, it's a mess, but there are efficient algorithms to do that. Again, by Katrin Klamroth and co-authors. Okay, now this is actually the upper bounding set UB that we were looking for, right? We can use that. Yn, our non-dominated set, is a subset of this set, right? And now we need the lower bound. This comes from these subdivision arguments somehow, right? So we haven't looked at subdivisions of the feasible set yet. Now we need to introduce that. Again, we subdivide the feasible set into m primes, right? So then we also, this induces a subdivision of the image set, like this one here. And now we want to know maybe if we can remove the set m prime, which leads to this image set here, right? So this is far away from the set of non-dominated points. So then there should be some way to remove that. These are the so-called discarding tests, which remove m prime. And how can we decide to do that? So how did we do that in the single objective case? So a point, a set m prime can be discarded, like the one in the picture, if the minimum of f on the set exceeds the current upper bound. There's again a set formulation for that. Singleton UB does not lie in the upper image set of m prime plus r plus, which would be the set here, right? And UB is outside of the set. So the guess is in the multi-objective setting, M prime can be discarded if our capital UV, which are these local upper bounds, do not intersect with the upper image set of f of M prime, or of M prime. Right? So adding Rm plus to this thing here gives you the shaded set. And this is actually true. Right? So this is already also something which is known already. So that's a discarding test. The only problem with that is if you want to check algorithmically if this intersection is non-empty, you need a tractable description of this upper image set. And this is done by relaxations of this upper image set. But again, this is something that one knows already from single objective optimization, because you don't really try to compute the actual minimal value of f on M prime, but you compute this lower bound LB prime by convex relaxation or something. And then you use the sufficient condition. If LB prime exceeds UB, then of course you can throw away, discard the set M prime. The same thing can be done in multi-objective optimization. So you can introduce a compact partial lower bounding set, LB prime, with the corresponding property, namely that the upper image set is contained in LB prime plus Rm plus, like in the picture. And we call LB prime a partial lower bounding set. And of course, if this set doesn't contain any local upper bounds, we have a sufficient condition for the discarding property. Right? So M prime can be discarded if this tractably checkable condition holds. And where does this LB prime come from? So first idea from Fernandez and Todd, for example, they didn't know the local upper bounds. They used it somewhere else, is interval arithmetic. So by interval arithmetic, you can compute a box, capital F of M prime, which can be quite coarse, but definitely contains the image set F of M prime, small f of M prime. And the lower left corner here, this is your set LB prime. It's a singleton. And you see already, this is so coarse that it doesn't give you good results sometimes, because now one of the local upper bounds is inside the set and you couldn't discard M prime, although in the picture you see that it's possible. So there are other ways to do that. For example, as I told you, Gabi Eichfelder and Julia Niebling introduced alpha BB techniques to do that. So you do a convex relaxation of all the involved functions, the objective functions f, and also the constraint functions g. And unfortunately, the image of a convex set under convex functions is not again convex, but the upper image set is. And then you can again have a tractable description of a relaxation here, and you can check whether these local upper bounds are inside. In our paper, we also introduced a third discarding test that I will not explain here, based on a reformulation-linearization technique. Okay, now let's say we have a way to discard these sets. Maybe this one is discarded now, and many others too. And for the rest of the sets, we tried to discard them, but we were not able to. But during this discarding tests, we computed some more feasible points and their image points. Right? The black points are new image points. And now the next step is, of course, we can update our provisional non-dominated set by looking at the new image points here. I go back one step. So the black points were the old provisional non-dominated set, and now we have some more. And if we only take the non-dominated among them, we have a better approximation already of the non-dominated set. Of course, this induces a new set of local upper bounds as well. And well, then for all the boxes which have not yet been discarded, we have some partial lower bounding sets. That we used them for the discarding test. The discarding test didn't work. Let's say singletons for this talk, to keep things as simple as possible. Many more, of course, right? So these are certain partial lower bounds corresponding to boxes which are still in the list. So there are many of them. And now, what is done so far in multi-objective branch and bound is you look at all the boxes from interval arithmetic, for example, corresponding to these points. And you say, okay, these form a covering of the set of non-dominated points, and termination criterion usually is all these boxes should be small, right? Then they should form a good covering of the non-dominated set. But this is not at all consistent with a single objective branch and bound idea. There's no sandwich, nothing which is thin or something. And so we suggest to do something else. Why not look at all these green dots and take their non-dominated set, would be this one. And that's the overall lower bounding set. So an object which has not been introduced yet in multi-objective branch and bound. If you add the non-negative orthents, you get a set which contains the non-dominated set. You have this upper bounding set. And actually now we have an enclosure E, which really sandwiches the non-dominated set, right? And here's the first result. So this is really true. So the non-dominated set lies in this enclosure, and also the provisional non-dominated set lies in this enclosure. First theorem. Now we need a width measure for this enclosure. And what we suggest to do, and I'll give a justification for that in a moment, what we suggest to do is to measure this width along diagonals in 2 dimensions, so along this direction E, the all ones vector. Right? You just pin through this enclosure and check how long are these black lines. So in a formal definition, you get the maximum of these distances of 2 points where y is in the enclosure and y plus te is in the enclosure. T can be chosen to be non-negative due to symmetry. And we have a normalization constant here because if you do the calculation, of course, you see the objective function is just t then. So why is this a good measure? The first thing is it can be calculated very easily, not by definition, but by the following observation. The enclosure can be written in a different way. If we build it by these singletons, the upper bounding set is built by a finite number of red points, the lower bounding set by a finite number of green points, then the enclosure actually is a union of boxes which are made up of lower bounding, lower left vertices and upper bounding, upper right vertices, right? So for example, this bluish box here, this one, and this one correspond to this point here. You cannot use the other red points together with this green point because you don't get a box then, right? So that's this inequality here. And you do this with all the green points, you get all the boxes. And now what we need for our width measure is the shortest length of any of these boxes, which is quite a strange condition in branch and bound. You usually look at longest edge length. Here we look at the shortest edge length. And once you have defined that, we have a lemma which says this distance measure that I just introduced can be computed as taking the maximum over all these boxes of their shortest edge length. This is exactly the width. Right. Now you can compute that. It's just a finite maximum, and if this is below epsilon, you should get something reasonable. And this is actually the justification for taking this width measure. You get exactly the analogon to what you have in single objective branch and bound. If UB minus LB is below epsilon, you remember, then you have an epsilon minimal point. And here you get all the black points, and the points in the provisional non-dominated set. Now they are epsilon non-dominated. That's a justification for this width measure. What is epsilon non-dominated again? That was this picture. So that's the natural termination criterion for multi-objective branch and bound, something which hasn't been around yet. Right? So our theorem 2 is the termination criterion, epsilon, the width below epsilon. And then the provisional non-dominated set only has epsilon non-dominated points. Also, you get an idea how to select the next box M prime that should be branched in branch and bound. That's the node selection step, because if the width still is above epsilon, you take a box which is responsible for this big value, right? So you take like this box here with the longest, shortest edge among all boxes, right? Because the width is the maximum of all the shortest edges. So first you identify such a box, and then corresponding to the lower left corner here, to the A, there is a subset M prime to which this A was the lower bounding set. And you take this set M prime and branch it. So for example, now you subdivide here, you subdivide in the decision space, and here the effect in the image space is the subdivision. You compute new partial lower bounds, these two, and maybe you also have to update the lower bounding sets. You also computed some new feasible points. You get feasible image points. You can update the non-dominated, provisional non-dominated set along with the local upper bounds and so on. And you see that the enclosure becomes thinner, right? That would be the branching step. Big question is, does this really converge? Well, and we have a convergence result in the paper. That's the next theorem. You need something about lower bounds and something about upper bounds. They should do the correct things for convergence. Now, if you do the lower bounding steps here by interval arithmetic, by alpha BB, by this relaxation-linearization, reformulation-linearization technique, or any other, in some sense, convergent procedures, then the lower bounds do the correct thing. And for the upper bounds, we just need that feasible points can be computed when they exist. So of course, in empty boxes, you cannot compute feasible points, but in non-empty feasible, partial feasible sets, M prime, which have a box constraint and a non-convex constraint G less or equal to 0, it's not always clear how to identify a feasible point there. And the condition is you must be able to compute a feasible point somehow, that's all. Then this branch and bound idea terminates after finitely many iterations for any epsilon that you as the user suggest. Now we did some preliminary computations to see if this works at all. So there's a well-known problem, a test problem, multi-objective optimization, which is called the Fonseca-Fleming problem, non-convex problem. Here we see a part of the image set. This is just generated by taking a coarse grid in the decision space and plotting the image points of these grid points. Right? This is what you get here. So you get an impression of what the image set looks like here. Still a bi-objective problem, of course. And this is used in, as a test problem a lot because there's a formula for the non-dominated set here. So here, in that case, the green one is the non-dominated set. And what does our algorithm produce? So here for epsilon being 0.1, this is our provisional non-dominated set. It even is quite nicely distributed along the non-dominated set. If epsilon is 0.05, you get more points along close to this non-dominated set, right? And what about these enclosures? These boxes that we computed here look like that, for epsilon being 0.1. And if you have time, you can check if the shortest edges of all these boxes really are below 0.1, but you have to check that these scalings of the axis are different here, right? So they really are, right? So the smallest edge length of these boxes is below 0.1. Another example, which looks a little complicated, but it's constructed in such a way that you get a nice effect in the image set. Again, so this gives you an impression of what the image set looks like by plotting image points of grid points. what does the non-dominated set look like here? It's a little different now, because you start here with non-dominated points, so all these, not the curl over there, all these are non-dominated, but the set stops here and it starts again over here. Right? So the non-dominated set has a gap. The points in between are not like this one. That's not a non-dominated point, because you can shift it to the southwest, and both objective functions get better, right? That's not a non-dominated point. You have a gap. Now this is our provisional non-dominated set. You see the gap for epsilon being 0.1, for 0.05. The approximation gets better. And now what happens with our boxes? Something strange. But this has to be expected. So in this box covering of the non-dominated set, you don't see the gap. You only see very lengthy boxes here. But this has to be the case because we have to have some local upper bound at this point, which is generated by these images of feasible points that we have over here. So you cannot get rid of that, right? So there are these lengthy boxes in here. And in general, what one can expect, and these are not results now, only conjectures. So this is the open question slide, number 100 now. So what we expect is that our box coverings converge to this set. Now again, in my toy example here, what kind of set is that? So you see already there are also these lengthy boxes here, like in the numerical example. And this is actually a set related to the upper image set, not to the image set. The non-dominated set is a part of the boundary of the image set, but of the upper image set. So where everywhere you add this non-negative orthant. So you get these points, for example, because we add a non-negative orthant over here. That's part of the upper image set. And the weakly non-dominated set of the upper image set is this blue line. And our conjecture is that our box enclosures converge, maybe Hausdorff distance or something, to the set. And it would be interesting to know properties of the set, like, is this always a connected set? In the examples, it looks like as if this was the case, but for the non-convex setting, there are no results known about that. We also don't know if our enclosure, this union of boxes, is always a connected set. It could be disconnected by definition, but we didn't find a good argument to show that it's a connected set. And in higher dimensions, of course, these connectedness results become even more involved. You can have a connected set with holes. Guess is, well, but there aren't any holes. So this is future work that we haven't looked at yet. So these are some open questions. I have one last slide with some of the literature that I cited, and that concludes my talk. Thanks very much.
Thank you very much for the very nice talk, Oliver. We'll go to some questions now. I noticed there's already one in chat, but before I go to Marco, I have just one very quick one. In the very beginning, the problem you posed had this constraint given in terms of G, which was assumed continuous. And my question is, it seems like a lot of the things that you talked about didn't use the properties of G very much. So is it just simply enough, or is it just the fact that the lower level sets of a continuous function are closed that is being used? So in other words, that lower level set is closed? Is that the important property here?
Yes, partly. So the main, so from a topological point of view, the closedness is important, in particular the closedness of this image set that we see here several times, because this gives rise to a property which is called external stability. And external stability means, and we use external stability several times in our proofs, external stability means that when you have a point in the image set, it's either a non-dominated point or it is dominated by a non-dominated point. And so this point is in the non-dominated set, and this one is dominated by a point in the non-dominated set. And that's not always the case if the boundary is missing, right? If your feasible, if the image set looks like this, there is no non-dominated set at all, right? And not all the points in the image sets then, there aren't any points in the image set which are dominated by the non-dominated set because there's no non-dominated set. And so this is external stability that we need here. And there's a second reason, algorithmically, if you want to do this discarding tests, that's why I'm looking at this slide now here. If you want to do the discarding tests, you need to compute somehow if a local upper bound lies in this approximation, and you have to compute the approximations, and all of this needs some good properties of the functions G, like the alpha BB method needs that the functions are even twice continuously differentiable so that you can control the curvature. And well, yes, and for this auxiliary problems that you solve, then of course you also need some usually algorithm from nonlinear optimization to solve them, which need continuity. So I hope this answers the question.
Yeah, thank you. So yeah, I'll go to Marco then. Marco, would you like to ask a question?
Yes, me?
Yep.
I wrote something in the chat. Well, first of all, congratulations, Oliver. It's a wonderful talk. You proved that it's possible to explain mathematics online, but you need to prepare in advance 101 slides. Sorry, so it's a great task. No, but it's clear that the ideas can be presented in a wonderful way. Very. Congratulations. But my question concerns the numerical complexity. First of all, I think that approaching one so general problem is global, non-convex, multi-objective optimization is a very ambitious goal, no? It's clear. And so my question is, what about the numerical complexity, and which is the limitation about the number of objectives? 2, 3, 4, in principle.
Yeah, so of course it's not possible to do things efficiently here in a complexity sense. This is not even possible in a single objective case.
Okay.
So you cannot expect that in the multi-objective setting. So one is happy if you can compute anything at all in finite time. Of course, everything is much easier for the bi-objective case than for more objective functions, right? So in the dimension of the decision space is not so much the problem, because all the computations, most of the computations are done in the image space somehow. Of course, these checks here, the local upper bound is inside the set or not, also needs a problem which has a decision variable x if you compute that. But then the main things which slow down the process are happening in the image space. And as I mentioned already, the computation of the local upper bounds is very easy in the bi-objective case. It's just you take the black points and then swap the second coordinate. So this local upper bound has the F2 coordinate from this point and the F1 coordinate from this point. And you go through the set like that, you immediately get this local upper bounding set. For 3 objective function, that gets completely messy. So Katrin Klamroth has very nice 3-dimensional pictures of what that can look like. But they came up with quite good updating formulas for this local upper bounding set that don't take forever to compute. if you do this for more than 2 objective functions. So we need updates of the set, right? We update the provisional non-dominated set by a couple of points, and then the local upper bounding set is also updated. So there are good algorithms for these updates. Then we need to compute non-dominated sets of finitely many points in several places, like among the black points or among the green points, like in this picture here, from here to here. This has to be done somehow. If these lists of points are very long, one should not do this by comparing the pairs of points. That would be a possibility to find the non-dominated set, but there are also more intelligent algorithms to find the non-dominated set, like an algorithm by Gref, Jahn, and Younes, which does that in a more efficient manner, but efficient always in the sense quicker than if you just do it ad hoc. So in terms of complexity, you cannot say that one can do things here in polynomial time.
Okay, thank you very much. Congratulations again.
Thank you.
Okay, I noticed that Janos has a question.
Yeah, so there are other techniques for the same problem by people like Delnitz, for example, and they do what they always do. They reformulate the problem as a dynamical systems problem where what you're looking for is the attractor, and then they use their subdivision algorithm to find that attractor. I think this is work from 2005 or something like that. Do you know how this compares complexity-wise to what you are doing?
No, not at all. So actually, I don't know the approach. The dynamical system whose attractor is the non-dominated set, right?
Yes. So basically, you're looking for, it's a bit like scalarization. So you're looking, in your language, you're looking for the scalarizations that would drive your point more towards the non-dominated set. And then you just do a subdivision approach on the dynamical system that you get from that. And well, they have an efficient algorithm, reasonably efficient algorithm to compute the attractor of this. Okay. But I think they are working in the primary space, so they are looking not in the image space. So that may be where you have an edge.
Okay. Yeah, I have to look at that. Can you tell me the author once again? Dan?
It's Michael Delnitz from Paderborn and a few others.
Okay. Yeah, thanks very much. I'll check that. I have to mention at this point that we do not really do a scalarization approach, which is also possible in multi-objective optimization, which means that you, instead of the multi-objective problem, you try to solve a single objective problem. And the most common scalarization approach, of course, is to look at the weighted sum, weighted sum of the objective functions. There are also other scalarization approaches. And then one could just use the usual branch and bound method from single objective optimization on this scalarized problem. But there are the usual drawbacks of these scalarization approaches, like for the weighted sum, you don't know which weights to choose or how to change them systematically and so on. So our line of research is more transferring the branch and bound ideas directly to the multi-objective setting and not using them on a scalarization.
Okay, so it's 6 o'clock now. I don't see any more questions, so I think that's probably a good time to finish up then. And so thank you again, Oliver, for this very nice talk.
Thank you.